The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'd like to introduce David Shuk. He's Associate Director at SOM in San Francisco. And he's going to talk about increased reliability and cost effectiveness with performance-based seismic design.
I think the title changed at some point along the way. I apologize for that, but it's still the same building, just different title. So the focus will be on proportioning for slender, tall buildings. As we get pushed into those more and more in residential buildings, it's a challenge, especially with situations like that was just talked about with near fault in Hayward. It's very important. So the agenda, we'll talk a little bit about clarity of structural systems, some critiques on some of the things we find ourselves into and maybe what we should be doing. Nonlinear analysis as a design tool. There's positives and negatives to that. Expanded use of response history analysis for design of force-controlled elements. There's some proposals there. And then torsion, we'll talk about that and how that's not well predicted by response spectrum. So this project is used to be called TRANSBAY Block 9. Now it's called 500 FOLSOM, 40-story residential building. It's a really nice improvement to the city. There's a collection of buildings, several of which were done by MK, but this one's situated there in the middle of it on Folsom Street. So a few quick facts. It's 400 feet, as many other of these buildings are in San Francisco. It has a tall podium that's very influential to this behavior. And a very, very deep basement. We're not sure, but we think it's the biggest one in San Francisco. At least that's what Balfour Beatty says. Either way, it's a bear. It's quite large. So some key other attributes of it is at the top of the podium, there's a greenscape and amenities area, which is very important for the developer and the sale of that. And then also, again, just a very deep basement in dealing with that. So clarity, how do we do structural systems? Depending on if we're in-house with the architect or not, or where we're brought in the design phase, we have different influence on this. But I think many of us who are doing performance-based seismic design are seeing the critiques of some of the things that we did in the past that we got away with in terms of response spectrum. Some of those things are not looking very nice anymore. So, you know, core plus walls, sometimes we have to do it, I get that. But core plus moment frame, that's basically gone. Web walls, my friends in SOM Chicago do that, but we don't like to do that. So I don't know, maybe not. Maybe we should just be trying to do that. And in order to do that, we really got to work with our architects very, very closely, of course, because this doesn't always work. Sometimes we need a little more gas. But in trying to get that to work, we also have some additional tools with performance-based design in terms of enhanced understanding of the building and enhanced ability to respond to that understanding. It's a little hard to see, but that's the architectural floor plate. The main thing to point is that everything's collected inside the core to try to maximize that and also minimize its penetrations. And then all of the units are around. They're nicely organized with columns and heat pumps. We have a very clean building and a clean structural system. Early on in the design, we did not have that. We had a more rectangular shaped core, as that was kind of the result of what the architects were giving us. During schematic design, there was quite a bit of back and forth to try to work this out. And we were seeing 3.6% drift under MCE, at least with some of our initial models, and we really just were not liking that. So we had to draw these outriggers. We hated them. We knew we needed to find a better path. There's nothing wrong with outriggers. It's just for a 400-foot building. You shouldn't be doing that. So this was I'll kind of skip past this. It's a little bit of a novelty, but in terms of looking at outriggers, there are some interesting ideas with topology optimization looked at in post-tensioning. It's a really nice academic exercise, but ultimately what we really wanted to do was get that core size just a little bit bigger, and we got it down to 12:1, which is a little bit more comfortable for a 400-foot building. Initially we were looking at SRC link beams and DD. We later took those out in favor of diagonally reinforced link beams. But also the podium, and this kind of gets into that commentary of response spectrum and torsion. You know, when we designed this podium, we proportioned the podium build walls just to supplement the added seismic mass in the podium. They were not intended to really help the core on its own, just enough wall to deal with the podium, let the core deal with everything else. and then a mat. It's not on piles, even though it's down at very good soil and a sand layer. So a 10-foot mat and a 5-foot mat outside of that. So the final design maintained that 33-foot depth in the core, which worked pretty well. Aspect ratio of 12:1. Pretty typical. Everything else, material strengths, member dimensions, all that's pretty typical for these types of buildings. Diagonally reinforced 8,000 psi concrete. So those are elevations of the 4 cores. You can see the boundary zones are a little bit darker, so it's a little bit easier to read. But you can see that at least in the slender direction, it does get pretty slender, especially at the top of the podium going up. So in early design, all we used was response spectrum. Very good, we think, behavior. Torsion was down in mode 3. Mode 3 was well separated from mode 1 and mode 2. We would think, we're not going to have any torsion problems in this building. Well, and many times that's true, but for slender buildings that are going to go through high ductile behavior, that's not always true, and we saw that later on. So again, some of the fallacies of response spectrum. Again, just showing the drift was comfortably below the 3% for MCE response spectrum during design. Didn't have any issues with drift when we were doing response spectrum. So when we got our ground motions, you could say, well, that's part of the problem, but there's a lot of variability in ground motions. So this is actually the short period suite, which actually controlled the design, which is a little frustrating. It's usually the long period. And the reason being that is, we had a couple of ground motions and we belly ached and belly ached and belly ached, but eventually we ended up with these 2. There's actually another one behind it, 3 ground motions there, that in our target period out here, even though it's a short period range, and it really had to do with just some reflection. We did we had 3 CMSs, we combined 2 of them. Probably not the best idea, but that's what we did at the time. And this is kind of a pictorial diagram we like to use for bias evaluation to make sure we don't have too many ground motions going in one direction, especially in San Francisco, theoretically far from the source, but 41 may change that. So in terms of nonlinear modeling, it was a very comprehensive nonlinear model. All of the columns were modeled. All of the slabs had nonlinear hinges. This was a very, very robust nonlinear model. You could say it's maybe too robust if you want, but that's fine. Obviously fiber elements for the shear walls, more densely packed in the boundary zones than not. And then we used the Naish tests for the link beams. Although we did elect to use the Naish test that included the RC slab because it had a little bit more strength and we needed that for the slender core and the high rotations of the link beams. But we did not include the slight more benefit if you do link beams with, this is all about nonlinear modeling, right? It's just whether you include the slab or not include the slab and whether the slab is post-tensioned or not. But that was beneficial in terms of demonstrating a little bit more strength in the link beams than we would have had otherwise. And also very detailed modeling of the strain actually at the face of the wall through a little outrigger element. So one of the things that we reflected on is early in the design, I tried something new. Okay, we always try to do new things and we have a little bit of liberty in terms of R factor. There was some papers published and they talked about lower R values, and we think those are good for the force controlled elements, but in the initial design it was actually an R of 3. We thought that might help a little bit with the stiffness. A little bit more rebar, but help with the stiffness a little bit. Wasn't really helping. In fact, we were probably paying for a lot of rebar that we didn't need in reflection of that. So we looked at the axial moment interaction from the nonlinear time history analysis, and those dots, if I can get my thing on, those dots represent response spectrum load cases. So you can see how we had this initial design out here, but when we did nonlinear time history analysis, well, it's nowhere near that. We're not yielding. That's not, I'd love to get more yielding of these things, but I'm not getting any, so obviously we're off base. So go to an R of 5 for the whole building for flexure. Shear still has a low R value. Force controlled elements still have a low R value. And then we try to make a hinge right in this zone and actually use an R value higher than code, which was demonstrated through peer review panel to be fine. But really try at the top of that podium to get some kind of hinge behavior to occur. So you can see there's a red zone going through. You can't see too much, but basically this is our hinge zone. Ground floor is down here. We couldn't get a hinge down there. Even if you put number 6's, like 0.2% in your boundary zone, you're still not going to get a hinge there. But we were able to get down to a little bit of a hinge here. And this first line out here, so this is total reinforcement in the core, all the vertical bars coming up. I recommend a plot like this if you're doing a core. And nonlinear analysis helps you understand how much rebar and where the cutoffs are. Out here, it was out at 2%. That's pretty high. That's pretty high. That was with an R of 3. With an R of 5, we got down to a little bit more conventional, closer to 1%, but we really cut that back pretty significantly there. Actually, peer reviewer wanted us to go out to here, and maybe that would have been fine, but having number 7 bars and number 6 bars in the hinge zone. At least some people weren't sleeping well at night, so we kept it a little bit more than that. So when you bring this up to an owner, they love it because there's a nice big reduction. Of course, everyone likes that. Based off of the changing the proportioning based off the nonlinear results is what we did, so that's good. This is kind of dense here, but I'll try to march through it. So this is drift kind of at the corner, and this is the 2% rebar scheme in terms of vertical rebar in the core. 1% rebar scheme where we cut that down quite a bit. And then at the hinge, when we cut it down a little bit more, and we actually increase the link beam strength, okay, over here. And you can see that when we had the 2% rebar scheme, we had 2 ground motions. Those are those troublemakers I mentioned earlier. Yeah, we're getting out over 4.5. We've got a real proportioning problem in this building. We fight with the peer review panel, but you know, it's a proportioning problem. Reducing the rebar helped a little bit, wasn't entirely part of the story, and then reducing it a little more, I think we finally got to a good point, and increasing the link beam strength. We had one go slightly over, and the peer review panel was fine with it. 716 says you can have one slightly out of, or one out of conformance. This was at 4.6%. It was just over the 4.5, so decided to let it go. So again, the kind of proportioning and reducing of the rebar to try to get the yielding that we want. So when we look at link beam rotations, hopefully some people are jumping up and down, they should be. On the first run with the nonlinear model, we had ground motions with strength loss in the link beam. That is not something we want to be seeing. That's even letting one record go over, I still would disagree. We don't want to be doing this. You can have some get out there in the strength degradation zone, but when you get to complete strength loss, that's a real problem. But when we go to the 1% scheme, it helped in the hinge area, but it didn't help with the link beams, so it really getting those, it's a little hard to tell, but all of those link beams are now right around the 6% limit, and only one of them gets out to a strength loss, and that was the one ground motion that went over on the drift. So again, one ground motion a little bit over, but the rest of them looking good. And again, it's just these 2 link beams on the end, in the weak direction going in the north-south that we're controlling there. So we look at strain demands. This portion of the core here, which is actually this portion right there and that portion right there. Whenever we think of these cores, if it's in an office and the link beams are deep enough, it is kind of a true core. The thing's acting as a unit. But when it's a residential building and you have these skinny little link beams, it's more of a confederation of parts, if you will. They're kind of talking together, which is why the highest strain is here and not necessarily there. So one of the things we did when we went to the 1% rebar scheme is we actually increased it at the top. I didn't talk about it earlier, but at the top there's a solid zone in the core to try to help with drift, and we adjusted the rebar there to help with the strains that we were seeing. And then, you know, as much as we try to get a hinge, you know, well, yeah, we got out to 2 times yield, but I wouldn't really call that a hinge. It's much better than it was. We had almost nothing before. But still, all of this higher mode yielding throughout the building is still very troublesome. And, you know, as an industry, we need to keep pushing for systems and methods that help mitigate that so we can focus and get more ductility in a controlled area that'll help with repairs after an earthquake so the repairs aren't systemic throughout the building. Getting into strain and confinement, you know, ACI 318, 14 has some really good criteria for that in terms of special and ordinary 6-inch spacing and 8-inch spacing. And we went on an endeavor, and, you know, sometimes we say that the peer review panel is, you know, sending an academic exercise our way. Well, we sent one their way just to kind of see what would happen. And we put some limits for strain out. And it's a little bit of a tricky topic, and I think this was actually really well discussed in 318 nonlinear on Sunday. And I think this is a really good topic. And, you know, there's a proposal there that we think is very conservative and rational, but we would really like to be more sophisticated with this. So it's a real challenge to the committees out there, I know, but if engineers can be more sophisticated with proportioning boundary zones based off strain demands, we can shave a few dollars, but we can actually be much more accurate. And I think that's really what we're interested in. So this is kind of a mapping of all those strain demands to different areas of the core in terms of which side of the boundary zone, whether we need panel zone ties or we don't. Do we need special reinforcing? Can we do ordinary 6-inch, ordinary 8-inch? Different criteria was set forth for all of those. And then based on that, you know, we have to put some panel zone ties up here where we have higher mode yielding. And then sometimes we need special confinement, like in this boundary, we needed it, you know, all the way over the top, we determined we wanted to do that. So again, just more targeted with how we are doing this, because the code, doesn't really recognize a core. I mean, I was having commentary with a colleague of mine, and, should we really have R values for cores? Because, well, they're not really what we say they are. We need to be much more targeted with these things, and especially when they're a confederation of pieces as opposed to one solid unit, which these residential buildings are more a confederation of pieces. I think we need to be more targeted. This is just good design in terms of designing panel zones at the top and bottom of openings. This one was really important because we had them at the top of the building as well to try to help with drift. Limited success on that, but only at the very high demanding ones was that really helpful. But we have to proportion them well, and we used the nonlinear analysis for that, and it came up with a rational basis. Because if you read the paper based off this, the design forces for these panel zones are the total capacity of the boundary zone, which is a huge force. It's very hard to design for. So if you use it based off section cuts, you can have a lower force that's a little bit more accurate and actually have a designable condition there in those panel zones at the top and bottom of openings. So this is, I just kind of step through this real quick. This is looking at the translation of foundation demands from perform into safe for design, which is very tricky. So these are kind of key points along there that we use for design, and I don't really want to get into this too much, but one of the hard parts is if you are transferring a global moment from perform to safe, how do you satisfy global moment in the core, moment in a wall, all of these concurrent forces that we want to design for. So this was a little multi-objective optimization to come up with a series of forces at different heights and different magnitudes so that we have the correct design moment in safe. Whether it's a global moment, the moment in the core, base shear at ground level, what have you, and we can actually concurrently satisfy all those with just one load combination, so that's kind of nice. So I think that's it. The last one was, torsion. I think we have to be really careful for slender buildings. We should be very careful about using response spectrum, because when we have very high ductility in these slender buildings, we need to be mindful that sometimes the ratcheting and strength loss can really affect the results. So if that's it. Thank you.
Anybody have something burning to typical late event?
Span to depth ratio, originally it was, I think it was 2.8 originally, but we actually widened the door to get the link beam to be longer to get the rotations down, and it went up to 3.5. So the depth was 22 inches, 9'3" floor to floor. Every project we do, it goes from 9'3" to 9'2" to 9'1", and at some point they'll stop, but they keep doing that to us.
I had a question.
Yeah.
How did you pick your envelope design points? I noticed you had a stop sign around.
Oh, how did we pick the axial moment interaction?
Yeah, for your foundation design.
Oh, for the foundation design. I could back up real quick. So there was an averaging done in each quadrant, and the maximum from the average, there was a statistical study done in each quadrant as the average, and then I think it was like 1.5 standard deviations out or something like that, to pick a point in each quadrant, and then they were mirrored, taking the maximum from each quadrant. So not actually my favorite method, but considering the translation between softwares, we're kind of in a difficult spot. Yeah. If we all get into ETABS, maybe it'll be better. That's what Ashraf says. We'll see.
Okay, thank you again. There's also one more question. Yeah. Scott.
What was the process you used to reduce the longitudinal steel in the core wall?
So the process was probably starting out with too low of an R value. That was probably the first one. But in terms of how much we could reduce it, each time, in theory, if you say you're going to reduce the longitudinal steel in the core wall, you should run nonlinear analysis, right? So how do you iteratively do that? You got, 22 ground motions and 3 weeks of analysis to get through. So what we would do is we would reduce it a fair amount and then run one ground motion, see how much it changed, and reduce it a little more, see if it would change. It didn't change too much, actually. So we eventually settled down to around an R value 5. We didn't pick an R value 5. We just reduced it until we found that one of the things that we looked at is how much yielding beyond there do you really want? I think we should have been more aggressive, but other people wanted to be a little bit more conservative, so only stayed around 7.5. Does that kind of answer it?
Yes.
It's actually not I would say it's almost non-answerable after looking at it a lot. But the question is, how much ductility do you want in your core, right? That's it's a tough question.
All right. Thank you.